last class of AMP 2. So what we're going to do today is review some of the anatomy, focusing on the blood flow in the digestive tract. That was complicated, and we're going to just review it quickly-ish. We'll see. Guided by your questions. And then we'll get into some whole body homeostasis concepts, trying to use homeostasis to remind you of certain key concepts from the whole course. So here is that slide that we looked at on Tuesday. Let's focus on blood flow. Going around with the laser, which I have recharged. Label something, anything. That isn't, that, I mean, stomach won't get you full credit, because it's his biggest day right there. But label something, but I'm mostly interested in blood flow, but if you want, but I'm not going to require that you choose an artery in this, or vein. Okay?
That is the lesser curvature.
The lesser curvature. This is, the stomach is inverted. Go ahead and pass it around.
Gastric artery towards the lesser curvature.
You gotta stop moving the pointer around so I can see if you're right. What's the name?
Gastric artery.
Yes, that's the left gastric artery.
Is this the celiac branch?
That this. Take your laser off.
Oh, I'm
Sorry. This is the celiac trunk. I
Okay.
think that's what you were labeled. It's this, which
Okay.
splits into three things. One of them being the one that that was labeled before, right, by Michael, left gastric. This is celiac trunk.
You got the right gastroepiploic.
Right gastroepiploic.
Left gastroepiploic.
Left gastroepiploic. It's all good.
The right gastric.
Right gastric. Can you read those words? I mean, it's labeled there, but I can hardly read it, so yeah, that's fine. That's the right, so right gastric, left gastric. Right gastroepiploic, left gastroepiploic.
This is the gastroduodenal.
So here, right in here is the gastroduodenal. When it splits into the gastroepiploic, the right gastroepiploic, and the duodenal. So this is the gastroduodenal.
Okay.
The artery,
Splenic artery.
splenic artery, going to the spleen and to the pancreas.
I don't think anybody named the abdominal aorta yet.
That's right, that's the abdominal aorta. Right there, that's the abdominal, this is the abdominal aorta, that's the abdominal aorta. Yep.
The whole thing.
The whole thing is the abdominal aorta. Yep.
Has this been said yet?
That one hasn't been labeled yet.
The hepatic artery?
That's the hepatic artery. Yep. We might be close to done here with, so let's just, I think we're done with the major arteries. So pick something else and tell me what its name is.
You can't see above here would be the greater curvature.
Yeah, sure, this is part of the greater curvature. Okay?
The pyloric sphincter would be?
Okay, so the pyloric sphincter is somewhere in there, yeah, between, this is labeled pylorus, so somewhere between the pylorus and the duodenum is the pyloric sphincter.
The portal
Yeah, the portal vein, that's the portal vein going to the liver. We'll talk about veins in a minute.
This is your.
That is the pancreas, but I already labeled that.
Oh, did you?
Yeah.
Okay. What have you not labeled?
Parts of the stomach. So we've got greater curvature, lesser curvature, pylorus and pyloric sphincter. What else?
Okay, the body.
Good, that's the body of the stomach. Who's got it? Okay, one more. Let's do one more piece of the stomach. Yeah. One more part of the stomach that you might want to be able to label. What am I thinking of? You can read my mind. Okay, there's the antrum and the fundus. Okay. Antrum leading to the pylorus, and the fundus is this big chunk over here. We don't see the cardia because the stomach has been flipped up and has made the cardia invisible. So it's still there. Remember this, hopefully you remember that this stomach is not in its anatomical location. The stomach has been flipped up so that we can see the celiac.
No, he definitely moved all the way around to here. Go like this.
Questions about this image?
That's the whole stomach.
Okay, let's talk about the arteries to the intestines. Some of these, only a few of them, are actually ones that I want you to know. Let me have the laser. What brave soul wants to label one of these arteries?
This is the superior mesenteric artery.
That's right. And this is the superior mesenteric artery. And we kind of saw it here. Here is the superior mesenteric artery sort of peeking out from behind the pancreas. And so what is not shown here, and what is not shown here either, is the hole, that it has to connect to the abdominal aorta. The orientation is that if we go here, we see that the connection of the superior mesenteric artery has to be somewhere in here. It's got to be somewhere in here because it's not up here. We would see it if it was up here. So it is below, it is inferior to the celiac trunk. So the celiac trunk is superior and the superior mesenteric artery is inferior on the abdominal aorta. Okay. So yes, this is the superior mesenteric artery. Anybody else want to label something else that you probably could guess the name of, knowing the name of this one? In fact, I'm thinking of this one. What is the name of this one? The inferior mesenteric artery. And we have not seen on the cadaver this connection. We just haven't seen it. All of these other things have names: colic artery, iliocolic artery. Here's the abdominal aorta again, and here's the iliac artery, the left and the right common iliac arteries. So some of those you've learned before, but the ones that I want you to know are superior and inferior mesenteric arteries. They provide blood to the large and to the small intestine. Okay, let's start with where it was. Label something else, not blood.
Not blood.
Not blood. Something else that we see.
So you can't label something like this.
I just gave it to you. That's the left common iliac. Okay, pass it along. No, it's going back. Or where is it going? It's going this way. Okay. You can pass because you were the brave soul that picked the superior mesenteric.
The appendix
Okay, the appendix. There's the appendix.
And then did you say this last that
No, I gave you that already.
long? The anus canal?
Okay, the anal canal is down there, yeah, that's true. Transverse colon, transversing from the right to the left.
Ascending colon.
Okay, ascending colon here, this part here has a different name, so we'll say starting around here is the ascending colon, from say, let's say here to here, ascending colon. This part here has a different name. Anybody remember?
Cecum.
The cecum. This is the cecum, this is the ascending, this is the transverse. Now we got an easy one coming up. Who's got it?
Cold garden?
Say again?
Cold garden?
Oh, it is, but that, okay, fine, I'll take it.
I didn't know. Wait,
Descending colon.
Descending, descending colon.
Ileocecal junction.
Ileocecal junction. Rectum. Rectum. I think there's one more that I would like you to hear the name of on this slide. But go ahead, you don't have to read my mind. No, go ahead and, oh,
I don't know
okay,
where it is.
okay.
That is the ileum.
Okay, if this is the ileocecal, that's a little cheap, but
Ileum,
that's
sorry.
true. This is the ilium, right? So this is the ilium leading to the ileocecal junction, but yeah, that's fair. I would accept, if I asked you to label something and you said if I said, give me 10 labels, and you said, well, this is the ileocecal junction and this is the ilium, I'd have to say, yeah, that's right.
That is the sigmoid colon.
Sigmoid colon, that's the one that I was thinking of. So sigmoid colon, S-shaped, that's where the sigmoid, it's S-shaped. Sigmoid. Okay, we're good? Now let's talk about veins, especially from the intestines to, and the stomach, to the liver, okay? Who's got the laser? But you just chose one. Pass it back. Okay, RJ. Okay, Michael? Any number. So, and I gave you the slide, and with numbers but not labeled, and so let's see if we can label the numbers.
Is there like a gastric thing?
Okay, 2 and 3 are the gastric vein.
Hepatic vein?
No, that's not the hepatic vein.
Okay, never mind. The inferior vena cava.
Hold the laser on it and let me see if you got it right. That is the inferior vena cava. This vertical tube here is the inferior vena cava.
Is that the portal vein?
That is the well, bless you. This is the portal vein until it splits here. So this here is the portal vein. Remember, blood is going to the liver. So from this junction here to the liver is the portal vein. That would be 16. 16 is the portal vein.
4 would be the splenic vein.
Okay, 4 is the splenic vein.
Is 7 the inferior mesenteric?
Yes, 7 is the inferior mesenteric vein.
And that makes this the superior.
Exactly, so 8, where is it? 8, no, not 14. Yeah, so 14 and 12, well, 8, 12, and 13. Let's see, what, 8, 12, and 13. 8, 12, that, Oh, so 8 is labeling colic veins, we're not gonna worry about that. 8, 12, and 13 are labeling colic veins, but 9, well, no, 7 is the inferior mesenteric, and 14 is the superior mesenteric vein.
5 and 6 gastroepiploic.
Yes. 5 and 6 are the gastroepiploic veins. Have we done everything? No, there's a few more up here. So portal vein,
I think so, yeah.
so this is the inferior vena cava. I think 17 and 18 are the only ones left. What are they? The name was mentioned in this room just a few minutes ago, but I said it was wrong. That is the hepatic vein. Those are branches of the hepatic vein taking blood from the liver to the inferior vena cava. Remember, the central vein of each lobule connects to the hepatic, to a branch of the hepatic vein, and the branch of the hepatic vein then takes that blood to the inferior vena cava.
But, so at line 15, going horizontal,
Line what, 15?
yes, but a little bit up.
Oh, I
Right
didn't
there.
even label that one. So I guess that one would be the gastroduodenal vein. Let's see, the answer key's on the next slide.
Wait.
Oh,
But I was asking the split, so the portal vein splits into the inferior and superior mesenteric right there. where-
right there is the junction of the superior mesenteric vein and the inferior mesenteric vein to form the portal vein. The splenic vein has already joined in, the gastroduodenal vein and the gastric vein has joined into the superior mesenteric here.
Okay,
I'm trying to follow blood flow. Remember, this is blood going up, not down.
okay.
So let's just see, did we get this right? 1 is the inferior vena cava, 2 and 3 are the left and the right gastric. 4 is the splenic, 5 and 6 are the left and the right gastroepiploic. 7 is the inferior mesenteric, yeah, we got that. We're not gonna worry about colic, we're not gonna worry about sigmoid, we're not gonna worry about jejunal, we're not gonna worry about ileocolic. None of these, so you can cross out 8, 9, 10, 11, and 12, and 13. So that just shows you that I'm teaching anatomy, but I'm not teaching anatomy as intensively as I could be. Right? Those of you who go on to further studies that require anatomy will get this, and you will be responsible for it, but this is undergraduate level. Right? So it's all good. So 14 is superior mesenteric. 15, we decided we're not interested in pancreatoduodenal. So what did I call it? Gastroduodenal? They call it pancreatoduodenal. We're not going to worry about it. 16 is portal. That's important. And the left and the right, well, hepatic veins. That's important. Clear what's important and what's not on a figure like this? Yeah.
So, with the arteries, you want us to know left and right, but with the veins, you don't care about that distinction, or?
Yeah, let's say that.
Okay.
Say it exactly that way. With arteries, I will hold you to left and right, but with veins, I won't.
So like if we have to label this left and right, each count as one.
No. On arteries, yes, and on veins, no.
Okay.
That's the logical extension of what I said. If you don't have to know left and right on the veins, you don't get credit for knowing left and right on the veins.
But arteries will give you two.
Arteries will give you 2 correct labels, left and right. Yeah.
Are you gonna want us to know more about like just labeling it or blood flow, like from an area to back to the heart, or both?
Both. Because labeling it is anatomy and knowing the direction and the path of blood flow is physiology. And this class has both names. Okay, we talked about water flow, let's not get into shit. Let's talk, when I used to teach in a medical school, and I used to teach physiology to medical students, and it was team taught by a group of, I don't know, 6 or 8 PhDs that would each teach a section of the course. And the director of the course one year when I was teaching it was this very proper English woman. She was a PhD scientist from England. And so the pattern of the course was very much like the pattern of this course. It ended with the digestive system, and the digestive system ended with the large intestine. And she just, I will not have my course end in shit.
He's awesome.
Wait, so what did y'all do?
I don't remember how she rearranged it, but she made sure that the large intestine and the rectum and the anus was not the end of the course. Okay, so let's talk about the questions about gastrointestinal blood flow in particular, or gastrointestinal anatomy and physiology. Let's go on and we'll see if something comes back. So I'd like to talk about homeostasis, just for a while. I mean, this is what so many of your physiological systems are trying to do. They're trying to maintain a set point. And so I've taught, some of you who have taken AMP1 have already seen this kind of analysis, because we do it in AMP1 as well. So the idea here is that there is a variable that is controlled, and it's got antagonistic control systems. So this all sounds very vague. Let's go to a specific example. In this room, there is a controlled variable, the temperature. The temperature is subject to control by the thermostat. I can raise the temperature, I mean it takes some time, but I could raise the temperature by cranking the thermostat one way, and I could cool the temperature by cranking the thermostat the other way. So the temperature has a set determined by the thermostat. Somebody has cranked it all the way up. Okay, so and the thermostat is controlling both a heater and an air conditioner. Something that cools the room and something that warms the room. So there is a set point, and let's just say the set point is a comfortable 70 degrees Fahrenheit on the thermostat. That's what the thermostat has set, and it controls power to either the heater or the air conditioner. Where's that laser? I want to use the brighter laser. So the point is, if the indoor temperature, if the room temperature falls into the cold range, let's just say somebody opened a window and the temperature fell because now there's ventilation, window, cold air coming in. The indoor temperature would drop, the thermostat would increase power to the heater and would decrease power to the air conditioner. More power to the heater would cause the indoor temperature to rise. Right? So this is power to the heater is high and power to the air conditioner is low, and that would cause the temperature to increase. And say it overshot. Say it, because the thermostat's not very good, and so the heater is cranked up, the air conditioner is turned off, and the temperature rose above the set point. Well, then the thermostat would realize, oh, but duh, I need to turn off power to the heater and turn on power to the air conditioner, which would tend to bring down the temperature. And so a good thermostat will control the power in a narrow range to the heater and to the thermostat, keeping the set point, sort of around, keeping the temperature around the set point. And it might oscillate above and below the set point depending on the quality and the quality of the heater and the quality of the air conditioner and the quality of the thermostat. Okay, so is that clear? When we talk about a set, so in this case, the indoor temperature is the control valve variable, and the heater and the air conditioner are what is controlled. The power is controlled. And I don't know how this is done, from an electrical or a HVAC perspective, but this is generically true. So we have the same thing with body temperature. We control our body temperature. It's around 37 degrees Fahrenheit. No, 37 degrees Celsius, 98.6 degrees Fahrenheit. So, whoops. Okay, so we have a way of setting 37 degrees Celsius. It's our set point for temperature control. If our body temperature were to fall, because we're standing outside in summer clothes, but it's winter outside, your body would increase a process of thermogenesis. And we haven't talked about thermogenesis, but you have ways to generate body heat. Shivering, there's shivering thermogenesis, your muscles making heat. There's non-shivering thermogenesis that your fat does. So your fat can make heat by doing non-shivering thermogenesis. There's a process called piloerection, where the hairs stand up and provide more insulation. We're not very good at this, but animals are real, feathers on birds and fur on dogs or seals, puffs out and provides more insulation, which is not a way of generating heat, but it's a way of conserving heat. So we have ways of making or conserving heat. And so if the temperature falls, we make more heat and we sweat less. And if our say we're running, say it's 95 degrees outside and we're running, we create a lot of heat. We need to get rid of that excess heat. So say our body temperature has risen because we're exercising in a warm climate, we will not do thermogenesis and we will do more sweating, evaporative cooling, right? So this is a pretty intuitive way of thinking about the physiology of a set point. And we could get into the details of this. The hypothalamus is important for integrating the information from your skin about whether you're hot or cold. Let's do something else. Okay, there's a I haven't talked about the cardiovascular system here, but I could. If your body temperature falls, what does your cardiovascular system do?
So
Go ahead.
slows down.
Well, we still have to beat a heart, so we don't want to die just because we're cold. But you use a word that was kind of close to what it closes something down. What does it close down? Constricts some blood vessels. What blood vessels would be constricted if your body is cold? Skin. Your cardiovascular system would constrict the arteriolar smooth muscle. And you should be thinking, okay, G proteins, constriction, right? I mean, constriction of arteriolar smooth muscle of the skin arterioles to constrain, to prevent blood from flowing to the skin and preserve core body temperature in order to survive. Okay, so what's the opposite in the cardiovascular system if we are exercising on a hot summer day? Vasodilation of the skin in order to provide more blood to the skin, in order to help the skin evaporate and radiate more heat. Now, we wouldn't want to prevent blood from flowing to the brain or to the muscles, so there would be a balance between how much vasodilation we would be allowed to do to get rid of the heat. And this is controlled by the hypothalamus. There's a thermostat in your hypothalamus. This is not testable. This is not material that I taught, but this is trying to integrate some of the material that you learned from the course with something you're already aware of: shivering, sweating. Okay, so let's do this with arterial pressure. So I think I gave you the blank one of this, didn't I? Yeah. Yes. Okay, so the set point for mean arterial pressure, remember it's systolic over diastolic, and there's an equation that you don't have to know for calculating the average or mean arterial pressure, but there's a set point, around 85 millimeters of mercury of hydrostatic pressure in the brachial artery. What goes up here, or what goes up here? Any brave person, how do we control, what physiological mechanisms do we have to control blood pressure And do we increase the power to it when the blood pressure is high, or do we increase the power to it when the blood pressure is low? Anybody want to start? Say again?
Stroke volume?
Stroke volume, yeah, but where would it go? If we increase the amount of stroke volume, is it gonna go in the upper left-hand corner or the upper right-hand corner? No. So, here's the logic. If the arterial pressure goes down, we would want to increase stroke volume. So we would, we would increase stroke volume in order to increase mean arterial pressure. What else?
Would systemic vascular resistance be?
Systemic vascular resistance would also go up here. If the arterial pressure went down, we would increase total systemic vascular resistance in order to increase pressure. So we would cause an increase in both stroke volume and total or systemic vascular resistance. What else? Going back to the cardiovascular system. Michael? Aldosterone, okay. So let's, tell me what you're thinking.
Retention of water itself, if there's more.
Okay, so we would increase the amount of aldosterone in order to increase blood volume. If blood pressure goes down, we would increase the amount of aldosterone to increase retention of salt and water, to increase blood volume, to increase blood pressure. Good. There are more. What nervous system would we activate here in order to increase blood pressure? Sympathetic. What nervous system would we activate up here in order to decrease blood pressure? Parasympathetic. Okay, so that's obvious. I mean, that's homeostasis. We talked about stroke volume and mean arterial pressure. Stroke volume and systemic vascular resistance. There's another one. There's a third component to the equation that determines blood pressure.
Heart rate.
Heart rate. Heart rate would go up here. If the blood pressure falls low, we would increase the heart rate by increasing the mechanisms for the sinoatrial node to pace the heart. And down here, so if the blood pressure is high, we might try to decrease heart rate, slow the heart. Okay, so aldosterone. Let's think of another way that we could increase blood volume. We've got aldosterone on the table. What's another way we could increase blood volume?
Hydration.
Okay, hydration, a drive to thirst, sure. There's another hormone that's important for retention of water. Vasopressin. So I'm not sure I got all of those, so here's my label. Sympathetic nervous system, the renin-angiotensin-aldosterone system, which is what Michael was getting at. Vasopressin all go up here, but we've talked about other things, right? Heart rate, that comes from sympathetic nervous system. Stroke volume also comes from the sympathetic nervous system. Systemic vascular resistance happens because of vasoconstriction due to the sympathetic nervous system. And here's the parasympathetic nervous system. So questions about the ways to think about homeostasis in this setting. What's clear is that as a group you were aware of things to control the heart and things to control the kidney. And the fact, what you should be pulling together for the final is the way the heart and the kidney work together to maintain a mean arterial pressure. And the way the sympathetic nervous system and the parasympathetic nervous system work together to maintain a mean arterial pressure. Yes?
So does ANP go with PNS?
Yes. ANP, atrial natriuretic peptide, would go with PNS. All right, let's do another, so, questions about cardiovascular and renal control of blood pressure. Things to review. Here's a slide that you might want to refresh your memory of, the flow chart for control of mean arterial pressure. So this flow chart is what happens down here. So we don't have to go through it, but we've got parts of it. Here's aldosterone. Here's the renin and angiotensin that led to aldosterone. Here's sympathetic nervous system. Here's vasopressin. These are all things you've seen, and you can do this flow chart. This will be up on Moodle, and you can sort of tell yourself the story of this. What's not on here is the parasympathetic nervous system because it's turned off in a setting of low mean arterial pressure. Questions about this? About this flow chart? I can walk through this whole thing using words instead of names and arrows. And if I ask you a question about the flow of, how we control arterial pressure, I see some of you taking a picture of the slide. It'll be up on Moodle. Don't just memorize the slide. Learn the concepts that are being illustrated by this slide, because I might ask you to tell me the story of, how does the sympathetic nervous system decrease GFR? How does the sympathetic nervous system therefore increase blood volume? And how does an increase in stroke blood volume produce an increase in stroke volume? Yeah.
So you could give us a question more like starting with the sympathetic nervous system, not just like, there's low mean arterial pressure, like.
I'm not sure I would. No, I might just say there's low mean arterial pressure. How do we try to maintain homeostasis? And I would ask, and a perfect answer would describe all of this. But, right, I could do that. Yeah, I could. You've seen my questions on exams that are kind of like that. And what my expectation for telling more than just one story, if there is more than one story that is to be explained. I might be kind and say, remember the nervous system and the kidney and the digestive system. Or I might do something like, well, let's go to the next one here. No, not this one. So this is just another reminder about cardiovascular control of blood pressure. This is just a reminder. Let's do this one. How do the lungs, how does the respiratory system and the renal system control blood pH? So the set point for blood pH is 7.4. We have mechanisms to control our pH at 7.4, even if we have a perturbation like eating a huge meal or exercising strenuously, we maintain homeostasis. So let's put up, what are the answers that go up on this one? And our friend, the Davenport diagram, which I could ask you to use again. So who would like to say where something that controls pH goes? Joey?
With the top left, the respiratory acidosis, and then the top right, the alkalosis.
Okay, well, so this whole part here, all of this is acidosis, and all of this is alkalosis. But we could have respiratory or metabolic. So this works, this way of thinking about it works for any acidosis or any alkalosis. What if we had any acidosis? What would be a response that would increase to try to fix the acidosis? Hypoventilation. So respiratory acidosis, increase in ventilation. So increase in ventilation would go up here, right? If we increase ventilation, we're tending because, let's just think of this, if the acidosis were respiratory acidosis comes from hypoventilation, and so if we wanted to fix that, we would increase ventilation. So what goes up here? If we have alkalosis, what would go up here? Decrease in ventilation. Okay? Yes?
Is there a specific term for like compensatory hyperventilation or hyperventilation?
There probably is, I don't know what it is. I would just say increase in ventilation.
Okay.
So, or compensatory increase in ventilation. That seems technical enough for me.
Okay.
Okay, so ventilation, increasing ventilation or decreasing ventilation would tend to, so increasing ventilation would raise the pH, and decreasing ventilation would lower the pH. I think I got that right. What else? Kidney. Excretion of bicarbonate. Which way does it go? Kendra, were you going to answer that? Okay, bicarbonate excretion.
Bicarbonate excretion would increase the acidity, so decrease the pH, right?
So increased bicarbonate excretion, increased excretion of a base would tend to acidify the pH. So this would be increased bicarbonate excretion, and this would be decreased bicarbonate excretion. Let's make sure I'm right on this before we get too deeply involved in this. So increased, the amount of bicarbonate excretion would increase here, and the amount of lung ventilation would increase here. And it flips on the other side, right? So increased lung ventilation, decreased lung ventilation. Increased bicarbonate excretion by the kidney, decreased bicarbonate excretion by the kidney. And remember that I like molecular mechanisms, so I will ask you for what is the mechanism by which we increase ventilation, right? Deeper respiration, a stronger contraction to the diaphragm, stronger contraction to the external intercostals, maybe stronger contraction of the scalenes and the sternocleidomastoid. That would increase ventilation. Increased rate of those muscle contractions would increase ventilation. What are some of the mechanisms for increasing bicarbonate excretion? Now we're getting into the bicarbonate excretion story. Decreased expression of carbonic anhydrase, decreased expression of some of those transporters in the kidney. Go ahead and review. Remember, this is sort of global homeostasis, but I could ask you for molecular mechanisms. It's part of my game. Not just a game, it's part of who I am. It's part of who you are now, frankly. And let's do one more, and that's, I think we'll be done early. We won't take a break. We'll just finish this up. Control of gastric pH. What are the hormones? So if the now we're talking about the pH within the stomach, inside the lumen of the stomach. It's got a set point of around 2. That's the set point for gastric pH. If the pH goes high, how could the pH in the stomach go high? Well, you just put a bunch of food in it, and the food is not, and that food was not lemon juice, that food was food, and so you put a bunch of neutral stuff in it, and so the pH in the stomach went up because the acid was getting buffered. Or how could the pH go more acidic? Excess of certain hormones. So let's unpack this one, and then we'll be done. Anybody want to put a control variable some variable that would increase the amount of, that would tend to raise gastric pH. Or alternatively, some control variable that would tend to acidify gastric pH. Brittany?
Somatostatin would be would be on the left side, and then gastrin and histamine would be on the right side.
Gastrin, histamine, and acetylcholine would go over here because more of those hormones cause the parietal cells of the stomach to secrete gastric acid. Somatostatin would go here because somatostatin turns off the parietal cells and causes them to decrease the secretion of gastric acid. Okay, what about secretin? Where would secretin go? It has an effect. I mentioned it. Where would secretin go? Let's see if I can figure this out. Secretin causes the pancreas to secrete bicarbonate. So secretin turns off gastric acid production. So secretin would go up here. Secretin turns off gastric acid production, and so does CCK. I think. Let me see if I got this.
Wait, but wouldn't that decrease pH?
Oh, you're right. So gastrin, somatostatin, CCK, and secretin would go here to turn off the production of gastric acid secretion, which would turning off gastric acid secretion would raise the pH. Let's see. Yeah, there it is. This is how your body controls these important set points. pH, stomach pH, blood pressure. Let's go this one here. So last week you ate a big meal. You put a lot of food in your stomach. So your stomach was stimulated to secrete a bunch of acid in order to digest that food. So your stomach secreted a bunch of acid. Your body went alkaline as a result of that secretion of a bunch of acid. Your body went alkaline as a result of your gastric acid secretion. So your body responded by, you may not have been aware of it, but you probably decreased lung ventilation. You might have been so full that it was hard to breathe, and that's kind of physiological, right? Less ventilation and increased bicarbonate excretion was part of that response to the gastric phase of a digestion of an enormous meal. And then later, as more and more food is going from your stomach into your intestines, your pancreas and your liver are secreting a bunch of bicarbonate. So your body is actually getting more acidified. And so we're down in here. We're down in this range. This thing that of the pH going, your body pH, your blood pH, going up right after a big meal, and going down in a few hours after a big meal, is called the alkaline tide. So if you were to eat big meals, the big meals would cause these waves of pH in your blood pH. It's like tides, right? Those of you who live by the seashore know that water comes in and water comes out, twice a day on the Atlantic. Anyway, That's another terminology. So I think we're done. We're done for the teaching. You're not done yet because you have a final exam. The practical quiz is available to you. If you're in the 7 p.m. session of the lab, you can come at 1 o'clock and take the quiz if there's availability. I have to give priority to the students who are in the 1 o'clock section, but if you want to come at 1 o'clock or 1:30 or 2 o'clock, you can. I'm going to do it in groups of 4. So basically, if 4 students, as soon as 4 students are ready to go at 1 o'clock, I will take those 4 students. And then again at 1:30, and then again at 2, and then again at 2:30, and then again at 3. Okay, so you can come to lab on the hour or on the half hour and hope to get into a 4-person session with the cadaver if you're going to take the practical quiz. The quiz has 36 pins, and you get 25 minutes, so that's about 40 seconds per pin, which is adequate. Okay, so I'll see some of you this afternoon, some of you this evening, and all of you on Thursday. What time is our final?
4:30.
Thursday at 10:30.
And this room.